let's explore the process of deriving the solution to the inner product integral in a little bit more detail. In the previous video, we determined that the inner product integral was given by the expression a equals 1 over t times the integral over 1 period of x of t e to the minus j omega t dt. And just to emphasize, the t that we're talking about, that's the period of x. Okay, so for now we're assuming that x of t is a periodic signal. In a few videos time we will remove that restriction, but for now that's the deal. Now, in order to work out what frequencies omega that we should try, again, we're free to try anything, but I'm going to be clever about which frequencies I select. I'm going to select frequencies, only frequencies, that complete integer numbers of cycles within 10 seconds. So for example, here you can see that that if we have a cosine here, I'm going to draw my cosine. Okay, it sort of makes sense that a cosine with a period of 10 seconds would fit to this, this signal. However, I'm also willing to argue that there should be a cosine at double that frequency within x of t. Okay, and the reason why I want double the frequency is that because x of t is periodic, that means that every 10 seconds, whatever cosines comprise x of t, all those cosines have to line up again. So you can see over here, however the cosines are lined up at t equals 3, they have to be lined up again exactly the same at x equals 13, 10 seconds later. If that doesn't happen, then how could x of t possibly be periodic? So we're only going to consider cosines that complete integer numbers of cycles every 10 seconds. So let's figure out what those frequencies have to be. We know that our period is 10 seconds, and therefore the frequency of the green signal, this one right here, the frequency of the green signal, the green cosine, has to be 2 pi over t, which in this case, t is 10 seconds. But this line of reasoning I'm explaining should apply for any period. Then I'm going to argue that no matter what happens, we only need integer numbers of that frequency. So in other words, I'm going to take 2 pi over t, I'm going to look for integer multiples of it. So n equals 1, 2, 3, and so on. Okay, and that will provide this property that I'm trying to get at, where the signals will line up every 10 seconds. So using this, let's go ahead and solve for a. So in this case, I'm going to plug in as many values as I can. So a equals 1/10 times the integral. Now again, it's going to be the integral from 0 to 10, but as we discussed in the previous video, there's only stuff to integrate between 3 and 4. And on that range, x of t is the constant 1. And then it's e to the negative j. And my frequency is going to be given by 2 pi over t times n. Okay, and that will give me my solution for any value of omega that's of interest to me. So 2 pi over t times n, and then there's a t, let's not forget the t over here, dt. And the reason I'm doing this is that this is going to give me the solution for any value of n. I don't want to have to keep resolving this integral every time I change frequencies. It would be nice just to do it once. And to specify, this is going to give me a sub n. Okay, so that's going to give me the nth value of a. So let's go ahead and, actually I guess I could replace this t. This t can be replaced with a 10. There we go, that looks a little better. Okay, so let's go ahead and solve the integral. So that's 1/10 times 10 over minus j 2 pi n times e to the minus j 2 pi over 10 n times 4 minus e to the minus j 2 pi over 10 times n times 3. Ugh. That's not exactly the prettiest formula ever, but we can take some relief. At least those 10s cancel. That's something. So there is a way to tidy it up a little further, but let's not worry about it for now. For now, let's content ourselves with the fact that what we have is 1 over minus j 2 pi n times e to the minus j pi n over 5 times 4 minus e to the minus j pi over 5 n times 3. Gross. Okay, it's actually gross enough that we can say gross. All right, but we can live with it. So what we're going to do now is we're going to evaluate this for a couple different values of n. So let's say n equals 1, n equals 2, n equals 3. And in theory, I can do any number of n's, but let's just start with those values. So in order to do this, we're going to open up MATLAB. And let's give this a whirl. So, oops. All right. So what I'm going to do is I'm going to basically attempt to type this formula into MATLAB, and then we will evaluate it for different values of n. Okay, so I'm at the command window now. So a equals @n. So this is what's called an inline formula, and it's going to be a function of n. So let's see, it's going to be e to the minus j times pi times n times 4 over 5 minus e to the minus j times pi times n times 3 over 5 divided by minus j times 2 times pi times n. Okay, and if I look to see what a is a function. So now I can say, what is a of 1? Okay, what is a of 2? And so on. Okay, so let's see. Let's start with a of 1. And that gives me an answer in form, in rectangular form, which is actually not of very much use to me. So instead of that, let's have it give me the absolute value of A1, which is 0.0984. That number should look familiar. I think we had it in the last video. So here we have A sub 1 equals 0.0984. And the phase angle is going to be, let's go ahead and have it calculate that for us. Angle is minus 2.1991. So minus 2.1991. And again, that's going to correspond to a frequency of omega 1, which is 2 pi over 10 times 1 radians per times 1. So that many radians per second. Okay? So let's repeat this process quickly for A2 and A3. So let's take the absolute value of A of 2. Oops, without the semicolon. The angle of A of 2. The absolute value of A of 3. And the angle of A of 3. Okay, so here we have A2 equals, where am I? I lost my place. 0.0935, 0.0935 angle 1.8850, 1.8850, and that's at frequency of 2 pi over 10 times 2, and N3 is going to be 0.0858. A3 equals 0.0858 angle minus 0.3142 at a frequency of 2 pi over 10 times 3. Okay, so let's let's go ahead and put all that together. So if we put all that together, here's what we find. We find that our original square wave contains, well, it contains a bunch of cosines, but at the very least it contains these three cosines. So let's go ahead and write these out. This is going to give me, let's see, don't forget that k is twice the amplitude of A. So in this case, it's going to be 2 times 0.0984 cosine of 2 pi over 10 t minus 2.1991. This is going to give me, let's put a little x there so it doesn't look like a decimal point. This is going to give me 2 times 0.0935 cosine of 2 pi over 10 times 2 t plus 1.8850. And finally, we're going to have 2 times 0.0858 cosine 2 pi over 10 times 3 t minus 0.3142. Okay, so our square wave contains each one of these three cosines. All right, so the last thing we're going to do is we're going to plot the sum of those three and see what we get. And that should actually, with just those three cosines, start to approximate the shape of x of t. So let's go ahead and give that a whirl real quick, and then we'll call it a day. So let's go back to MATLAB, and actually I'm going to open an editor. All right, so let's clear. So let's see, x equals 0, t equals linspace minus 20 to 20. Stick a whole bunch of points in there. Okay, a equals, actually we can just come back to our command line and find the formula for a and just copy it. So let me do this. Let's copy that. Copy. Oops. Oh, okay, paste. All right. So for now, I'm going to do this without a loop. We'll just do this sort of bit by bit. So x equals, so let's do the first cosine, 2 times the absolute value of a of 1 times cosine of omega times 1 times t plus angle of a of 1. And I guess I need to define omega equals 2 times pi over 10. Okay, so that's the first cosine. Let me write it like this. We'll make it a little easier to see what's going on. Okay, then we're going to do the second one, 2 times the absolute value of a of 2 times cosine of omega times 2 times t plus angle of a of 2. Is that enough parentheses? I don't feel like it is. All right, I think we missed a parentheses up here. That looks a little better. Plus dot dot dot. And we'll do the same thing yet again, except I'm going to get smart this time and do copy paste. Okay. Now I could do this in a loop if I wanted to, but for now, just to make it super explicit what I'm doing, I'm going to draw it out. Okay. And finally plot t comma x. And you can see that with 3 cosines, it's already starting to take the right shape. Okay, so let me go ahead and label that. Time, seconds, title, sum of first 3 harmonics. Okay, so now our plot looks a little better, and we'll paste that into our video, and we'll be done. Into our notes, I mean. Here we go. Okay, so here's what the sum of the first 3 cosines looks like. So why did we stop at n equals 3? No reason. In reality, what we need to do is go all the way out to infinity, right? We could do the 4th harmonic, the 5th harmonic, etc. And the more harmonics we add together, the closer this sum is going to start looking like the actual square wave that we wanted. But already you can see it has the right properties. It has a period of 10 seconds. And it has a peak that occurs between t equals 3 and t equals 4, which is exactly where it's supposed to be.